setting it up. And again, the only sort of tip I would have here is when you're choosing your torque, origin, your pivot point, choose it at a point where you have as many unknown forces acting as possible, just to make your life a little bit easier. Questions on this, or the sort of broader strategy of solving these statics problems? Yeah.
You also, for the net torque of the ladder about the
Mm-hmm.
do you also think the perpendicular components of each of the forces acting on it using similar triangles?
Take the perpendicular component of the forces acting on it. Can you describe that a little more for me?
So like about the pivot point, like the normal force, you have like the normal force, for example, you take a point that's like the component of the force that's perpendicular to the it's perpendicular to artificial, since that one's through the pivot point, it wouldn't matter. But,
Yeah, I see what you mean. Yeah, so again, this comes back to this idea that how you define torques is kind of up to you. Remember, we defined torque as the vector product of the R vector, which is the vector that points from the pivot to the point of action of the force. So it's R cross F, okay, where F is the force. So you can do it that way as well, if you want. You can make your force components perpendicular to the actual distance. So for this one, you can use that as R, and just look at the perpendicular component of this. Same with this or this, okay? So absolutely, and you'll remember I've said a few times, I'm not going to try and convince you which is the easier way that you want to do it. It's the same, it's equivalent, and I usually find once somebody's got the way in their head of doing it, try and make them do it with the other geometry is just confusing more than anything else. So it's the same, yeah. Yeah?
If you didn't have one piece of that information, would the way to solve it just be to have another torque equation and then make simultaneous equation?
Say it again.
If you were missing a piece of information, like one of the numbers, would
Yeah.
the way to solve it to set up multiple torque equations?
Possibly. Okay, so the question was, if you were missing, if you had fewer pieces of information, might you be able to gain that missing piece of information somehow by balancing torques around more than one point? So in principle, yes. Yes, you could. So that's a good observation. Okay. And in fact, once in a while, you will have a problem. Actually, it's good that you brought this up because it actually reminds me of the second thing that is good to know. Once in a while, there may be some ambiguity in a situation which can only be resolved by looking at net torque equals 0 around two different points. I can't off the top of my head think of an example of this, but occasionally you'll want to check net torque equals 0 about at least 2 points to make sure that it is indeed a viable static situation. Good, thanks for the question. Yeah?
In the previous questions we had with the ladder, the force from the wall is always has two components. Why is it in this one it just has one?
Simply because this is a smooth wall, right? I mean, if there was some friction at the wall, yeah, I'm going to add a friction component, which is going to be parallel to the wall surface. But in this case, I've defined it to be smooth. So if ever a surface is rough, yeah, generally you're going to have what you will decompose as a normal force and a friction force. Keep in mind that, and I mentioned this at the time, but as long as some of you may have forgotten, and maybe now it makes more sense. These are really two components of a single force, and we happen to define them kind of for convenience, so there's a little bit more than convenience associated with it. We happen to define it in terms of a perpendicular component and a parallel component, but in fact they are aspects of a single force, okay? Which would of course be the vector sum of these. Other questions on statics, and you're going to have a fair amount of practice as you finish out this week's homework on this. All variations on a theme, there's nothing new. Okay, good. So let me just briefly say a couple of words about center of gravity as opposed to center of mass. For us, center of gravity and center of mass are going to always the same point, okay? Center of gravity, well, let me come back to center of mass. It's kind of the position-weighted mass distribution of an object. And so if you have calculated the center of mass of an object, its, let me say, its position-weighted mass distribution is 0 around that center of mass point. So you've had a decent amount of practice associated with that. Hopefully at this point you're relatively comfortable with the calculations. Center of gravity is slightly different, but for our purposes, again, is going to be the same point. It's simply a question of what is the center of an object defined in such a way, first off, that gravity can be assumed to act solely at that point, and that gravity will simply exert what can be seen as a translational force on the mass about that point, so there's no rotation about it. And sort of equivalently, it's saying that there's no net torque about that point either. Now, why am I saying for our purposes they're the same? Formally speaking, when we're calculating the center of gravity, we're looking at the effects of the gravitational force acting on all mass elements of that object. If you happen to have a large object, so large in fact that its gravitational acceleration or gravitational field, some of you want to think in those terms, actually varies over the spatial extent of the object, then you will find that the center of gravity is in fact different from the center of mass, just because the influence of the gravitational field varies as you cross this rather large object. So for us, when we're treating objects in the constant little g near the Earth's surface, this is not something you need to worry about. If you are worrying about physics on larger scales, maybe where objects are experiencing different gravitational forces, or more correctly, different gravitational accelerations or fields over regions of their extent, you will find that they are not the same thing. So, a common trick, if you are wanting to use gravity to find the position of the center of gravity of some object, is simply to hang an object from various points. Let's do this quickly. Random shaped object. I'm going to hang it from a point near one of its edges. And if you think about this, gravity is acting on every mass element in this continuous distribution. So for every piece dm, there's a gravitational force dm times little g acting downwards. And once this thing comes to a rest, there's no net torque acting on this thing, so that's why it's at rest. So if you think about this, looking at a vertical line, passing downwards through that hanging point right now, that tells you that the net torque from all of the points on this side, which if you think about it, gravity is acting down, so everything on this side of that vertical line is tending to want to turn this thing this way. Conversely, everything on this side has a gravitational force acting downwards, and relative to this point, it's tending to turn it this way. So as soon as this thing comes to a rest, there's no net torque acting on this thing, and so this vertical line tells us that the center of gravity of this object is somewhere along that vertical line. Now I can easily take this and do this about another random point. Looks like this got busted up at some point. Here's another one. Hanging it here now, same arguments apply. Once this thing comes to a rest, the vertical line down there must pass through the center of gravity because there's no net torque on either side. All you need to do is hang this from 2 points that are not 2 points anywhere on this object, and those lines will cross one another if you define the center of gravity of that object. Okay? So just something to think about, an easy way to determine centers of gravities of objects. Hang it, draw vertical lines, look at the intersection of vertical lines, that's the center of gravity, okay? All right, so just a footnote on center of gravity. For some reason our lab technician had the same thing set up with a map of New York State. Curiously enough, if you do the same exercise, you can find the geographical center of New York State, which...
No Long Island.
Yeah, there's no Long Island, you're right. And in fact, I guess the reason this was selected is it's actually marked on here where the geographical center of New York State is, and it's slightly offset from where this point is just because Long Island is missing. okay? So, all right, all I want to say about center of gravity. So please take a look at a bunch of worked examples in my notes. They may be helpful in addition to the practice problems for chapter 11, just as you work through this, but I'm imagining most of you will find this relatively straightforward. Last demonstration on this before we turn our attention to deformable elastic materials. Has to do with the question of when objects may fall over. All right, so relatively uniform, I never remember the word of this thing, rectangular block. So by geometrical considerations, you know its center of mass, and in a uniform gravitational field, such as the one near the Earth's surface, its center of gravity is at the geometrical center of this object. So it's right in the middle of this if you were bisecting it along every side. Okay, right now it is in a static equilibrium. I can perturb it slightly, and an obvious way to maybe do this would be to tilt it, and it will be in a stable equilibrium up to a certain point, in the sense that if I tilt it a certain distance, it will go back to its vertical position up to a certain point. And of course, if I tilt it too far, okay. So that's defining the point at which it goes back versus falls over. What is it that determines, what is the angle that determines whether it goes back or it falls over?
The point at which the weight of the object acting at the center of gravity, the point at which it crosses
Good. Nice. Okay, so imagine a vertical line through the center of mass, center of gravity. If that vertical line, from your perspective, is to the left of that, let me call it a pivot axis, which it is. If it's to the left of that, the gravitational force acting on it is going to push it backwards, okay? Backwards. It's going to rotate it back to its equilibrium position. As soon as the gravitational force and the torque associated with it, as soon as that gravitational force line of action falls to the right of the pivot point, turning effectively now this way, and the thing falls over. Okay, that's the last thing you need to know about equilibriums, okay? So objects falling or on the verge of falling. Questions on statics? Okay, so end of our rigid object consideration. For now, we're going to turn our attention to elasticity and deformable materials. So let me clear off some space here. While I'm doing that, I want to remind you of this model I've mentioned a few times through the semester already of material, matter, in many respects being able to be kind of viewed as a kind of mattress-like assembly of masses connected by springs. Okay? So it's well-founded at the microscopic level because in many senses the forces between neighboring atoms or molecules can be treated a little bit like Hooke's law type forces. And that turns out to allow us to understand a little bit about elasticity and deformation. So again, here's my regular cuboidal, cubic lattice of atoms in some material. I'm not going to spend much time trying to draw this because it's never easy quickly. So there's some elements of a cubic lattice. Of course, they don't have to be cubic and rarely are in nature, but okay. So again, imagine what happens as I exert a force on some part of this three-dimensional. I'm not going to draw it anymore, it's already hard enough to see what I'm trying to get across. But imagine I'm trying to exert a force on some part of this mass spring setup. If these forces behave a little bit like Hooke's law, of course there's going to be a tendency to push back on those forces. And the question that we're going to address is really how strong those forces are, which is going to tell us something about the elasticity / deformability of that material. So, a couple of quick examples. Two types of rubber balls. Aside from color, they look kind of similar, but it turns out they are made of sufficiently different types of rubber that they have pretty strikingly different behaviors when they are deformed. So the way I'm going to deform them is simply by dropping them. Of course, when I drop them, they gain some kinetic energy, they gain some speed. Once they hit the tabletop, there's a sort of impact, there's an impulse, if you will, and the question of what happens is simply a response of the material to that deforming force. So if you think about this, let's take maybe this one first. That one bounces, okay? So in that sense, there's a fairly strong pushback as I deform the rubber of this ball. It pushes back, and it's the pushing back that allows it to bounce. This one, by contrast, does not push back much at all, and so it pretty much absorbs the deformation without pushing back as much. It doesn't make this thing bounce as high. So there's a more dramatic example of this with a couple of metallic balls here. They're not exactly the same size, but it's still kind of a nice illustration. Just now inside a tube so they don't bounce away. One ball, not so exciting. Again, it's pretty deformable, so it doesn't bounce hardly at all. And then by contrast, this one, which bounces a lot. Okay? So this is a varying degree of elasticity, and the response in terms of pushback determines how high, if you will, these things bounce. So let's see if we can characterize different types of deformations. Again, for those of you who are going to be engineers, particularly anything to do with mechanical engineering, is super important. So we're going to be talking about deformations. And in fact, we're going to be talking about the response to stresses, which is a slightly more technical way of talking about forces. We're going to talk about the response to those stresses. So strain, which is going to be a change in shape in some way, as a response to stress. Okay, so let me just highlight those two words, stress and strain. So this is an applied force. We're going to qualify it slightly in just a moment. And this is a response in terms of a deformation. Okay, so we're going to look at three different types of ways we can exert a stress on a material. And we're going to call them, let's see if I can remember this, tensile, shear, and hydraulic. So I think the easiest way I can visualize this is to take a certain shape of object, and I'm going to take something that's kind of maybe a cylinder. See if I can do this quickly. Here's a cylinder in three different situations. Let me do this one here. And last one over here. So it starts off as a cylinder with the same size, same material in all cases. And in the first case, what I'm going to do is imagine that this thing has a, let's say, a length here. and I'm going to apply a force that is maybe pulling this thing, so it's stretching it or attempting to stretch this thing. So this is going to be a geometry that we associate with a tensile type stress. I could also be compressing this, so tensile, I guess, might also, I think it's called tensile by engineers, I'm not sure if I get this wrong, you should tell me. So it's either a push or a pull, and we're going to be looking at the change of the length in response to this, to the exerted stress. The second case I can imagine is the same cylinder, so I still now have this thing with length L, but instead of applying a force that's in a sense along the, let's say the dominant axis of this material, I'm going to apply it sideways, and in this sense, it's going to be a so-called shear stress. And then the hydraulic one, I guess I'm going to keep L here just for consistency, but it's going to turn out something else is important. The hydraulic one, what do you think of when you hear the word hydraulic? And it may not be quite the sense in which I want to use it, but I'm just curious what you think of when you hear the word hydraulic. Hydraulic press. What do you know about a hydraulic press? Pushes things together. Okay. What else do you think of when you hear the word hydraulic? Incompressible fluids. Okay. Yep. Quite often. Anything else? Yeah.
Water.
Water. Okay. Hydraulic. Yeah. So what it really is referring to is a kind of overall pressure change exerted on something really in three dimensions, so to speak. Yes, it's usually a liquid. And so if you're exerting a certain pressure on a liquid, the kind of idea is that somehow that overpressure is exerted the same in all directions. And this will become more apparent on Thursday when we talk more about fluids. But the implication in this case is in fact that there's a kind of, I'm going to view this as an overpressure, that there's a kind of force being exerted in all directions, okay? And so really this is what we're going to talk about as a hydraulic stress exerted on this object. Yeah?
Exactly, if you define tensile shear hydraulic, if you were to put it
Okay,
into
so
words.
the question was how would I distinguish these and define them? I agree right now it's not very well defined. Let me just go a little bit further in terms of defining the response, and then we'll see if the distinction becomes a little bit clearer. All right, so let's take the one on the left, tensile stress. So I'm exerting some kind of force on this thing, and in fact, strictly speaking, the stress is not just the force, but it's defined as the force per unit area. Okay. So newtons per meter squared, for example. So that, technically speaking, is a stress. It's normalized to the area over which it's acting. Now the strain, remember I was talking about strain as a response to an exerted stress. This is the thing where we'll sort of color things a little bit and vary things a little bit. What we're wanting to gauge is the change in some dimension of the object in question. And so in the case of tensile stress, we will usually be looking at, let me write this for each particular case, tensile, shear, and hydraulic. Okay, so for a tensile stress, we are going to look at a tensile strain, which is simply delta L over L. It is the change in length of this object. So it's the change in size along the direction that these forces are being exerted. And again, this is, in this case, it's stretching, but it could also be compressing. It would still count as a tensile stress in this case. We're looking at the change in dimension along that force axis. So that's what defines a tensile strain. In the case of shear, okay, this is going to be something I should probably write on this. What we'll actually be looking at is not easy to illustrate without breaking a piece of chalk, so I'm going to exert forces on this thing in opposite directions at the top and the bottom. What we're interested in is how much, let's say, the top of this piece of chalk translates horizontally, namely in the direction of the exerted force, compared to where it was originally. So usually in this case, we are interested in that deformation. So it's the amount by which this thing again deforms, in this case in the direction of the applied force, but it is now perpendicular to, let's say, the length of interest of the object. So, again, these are all kind of useful simplifications, and the implication on your question is well taken, that, you know, in practice, the deformation is some complicated thing, but we want to parameterize it in simple ways. So in this case, it's along the length of the exerted force relative to the length of the object. Here, the force is perpendicular to the length of interest. Again, for engineers, these things are going to be important parameters. So the perpendicular displacement at one end, as I apply some force over the length. And then the hydraulic one is more interesting, because again, the implication here is that this force is in some sense being applied uniformly on all sides on this object. So usually what's interesting in this case is not a change of length, but in fact a change of volume of the object. Okay? So again, these are just parameterizations that are useful particularly for engineering context, where these are the sorts of things we need to know about materials and how they respond to forces if we're designing things and designing them to do that job. So let me just talk a little bit more about the relationships between these strain parameters and how we can relate them to the exerted stresses. But before we do that, I just want to give you some generic information about how a lot of materials respond regardless of the types of stress that's exerted. And this is coming back more to the sort of microscopic level of what's happening. So a generic stress-strain response. Okay. So stress on the vertical axis. It's not, in terms of cause and effect, the most logical, but it's still a useful way of representing this. So stress up here, again, is force per unit area. And strain down here, I'm going to take one particular example of a tensile strain. So delta L over L. I'm going to draw now a kind of generic type of response for many materials. This is not true for all, but it's true for many. Okay, so let's see if we can pass this and see if it makes sense. Okay, so start off here at the origin. This is 0, 0 in both cases. Write that to be clear. So I exert 0 stress on some object and I'm expecting 0 stretch. Okay, so we start at the origin as you would expect. Then as I start moving along this thing, I'm increasing the stress, the stretch that I'm pulling on this thing. And what you'll see for most materials is there's a linear dependence here. And that turns out to be a useful region to operate in. So it's an approximately linear response. So again, come back to our microscopic picture. This is basically where our Hooke's law type modeling of intermolecular forces seems to work pretty well. Okay? So think about that statement. Our Hooke's law type modeling of intermolecular forces seems to work quite well. Remind me quickly what Hooke's law tells us.
The force is proportional to the distance that something is displaced, or also as a function, negative.
Okay, good. So a linear restoring force. It's proportional to, or at least over the range that we say Hooke's law is valid, and most crucially, it's restoring, it's trying to pull this thing back. So that's exactly how we can represent intermolecular forces over a certain range, and it's represented